Hello again, folks. This is the second half of particles topic, this time focusing on solutions and separating techniques. This one had a lot of words, definitions, so I thought it might be easier if I just quickly went through the revision mat answers rather than writing out a mind map for you. So let's dive right in with the keywords that begin with S. So if you look here, there's quite a few words to remember about solutions. The first two are the ones that students always mix up. So solute is the solid that dissolves. That's the salt that we use, or copper sulfate, any solid that's dissolved. The liquid that does the dissolving is called the solvent. In our lessons, we usually use water, but there are plenty of other solvents like alcohol, methylbenzene. If you've ever done any painting in art class, you've probably used that to clean oil paints, that sort of thing. Soluble means something will dissolve. Saturated, we just came up in our acids and salts topic. Saturated is a solution that has the maximum amount of solute possible. So you can't dissolve any more solid, it will just fall to the bottom of the beaker. Solubility, this last one, is actually a number. It's the amount in grams of a solid that you can dissolve. And as long as we're talking about solubility, let's move down here to solubility curves. All right, so this often comes up on the test. They'll give you a graph like this where they show how the solubility in grams changes with temperature. So I've just written here a few questions that are common that might come up on your paper. First one, describe the trend shown by the graph. When you're answering trend questions, don't make it harder on yourself than you have to. Just copy the word from the x-axis and the word from the y-axis and say, as this one goes up, what happens to that one? In this case, the graph is increasing only, so it's really simple. As temperature increases, the solubility increases. That's all you have to write. If this was a straight line that went through the origin, you could give more detail and say it increases and it's directly proportional. You could give some extra data. But here, it's just a curve going up, so there's really not anything else you can say. Which salt is more soluble at 60? Right, now at cold temperatures, copper sulfate is more soluble. But at 60, if we go up, potassium nitrate is higher. So that's our answer. How much copper sulfate will dissolve in 50 grams of water at 100 degrees, right? So we go to 100 degrees, go up to copper sulfate, across 180. 180 is not your final answer, because if you read carefully, this question says in 50 grams of water, and our graph shows 100. We only have half as much water, which means we can only dissolve half as much solid. So we need to do 180, divide by 2 to get our final answer of 90. Okay, final question. This one is wordy and often students don't understand what it's asking, but it's actually not as hard as it sounds. If 80 grams of potassium nitrate are dissolved in 100 grams of water at 90 degrees, and the solution is then cooled to 20. At what temperature will crystals start to form? All right, so we start at 90 degrees, and if you go up, way more than 80 can dissolve. 200 can dissolve. So we're not even close to being saturated. It's great. We've dissolved all 80. Then we start to cool, colder and colder and colder. And the question is, when do you reach the point where 80 is your max? And if you get any colder, you won't be able to keep all 80 dissolved. Well, we need to go here to 80. And that's where most students go wrong. They focus on this 90 rather than realizing it's all about the 80 grams. And if you go across from 80, you get to almost 50. I think my line is a little off. Somewhere between 45 and 50. That's where 80 grams is your max. And if you get any colder than that, you can only dissolve 75 or 70 or 60. So at that temperature, crystals will start to form because all 80 grams will not be able to stay dissolved. All right. The second half of this, other than solutions, was about separating mixtures, often involving solutions. And this should be a nice review because we've just done the salt prep methods. So your first method is dissolving. If you have two solids, one that's soluble and one that's insoluble, you can simply add a solvent. The soluble one will dissolve, and the insoluble one will stay on the bottom. You would have done this with Mr. Beaumont at the start of the year when you separated salt from sand. by dissolving the salt in water. Second one, filtration. A couple keywords here for you. Remember, the solid is called the residue, and the liquid that goes through the funnel is called the filtrate. This is for separating an insoluble substance, solid, from a solution. So salt water from sand, or calcium carbonate, which is insoluble, from water. Third one, evaporation or crystallization. Keyword for you here, this is called an evaporating basin. That's sort of the white ceramic bowls that we use. You can heat the solution, all of the solvent, the water, will boil away, leaving you with your solute. So this is how you get salt from salt water. Simple distillation is next. This is if you want to get the water, the other half of the solution. So if you heat it, the water will evaporate. It will then condense in the condenser here and collect down here. We usually have a flask or a beaker at the bottom to collect it. Notice the water goes in at the bottom and out at the top. This is so that the whole condenser will become filled. If you put the water in at the top, it will just run down the bottom here and it'll skip the whole top section. We want this to be really cold so that all the solvent condenses into a liquid before it drips out the bottom. Fractional distillation looks very similar, except it has this column here. Hopefully you were able to see this at the beginning of the year. If not, don't worry, it very rarely comes up. It's really just an extra step before condensation to make sure that you've separated properly two different solvents. So you see this is for mixtures of liquids. This is most commonly used for water and alcohol because alcohol boils at 78 and water at 100. So you want only your alcohol to evaporate, and you want this whole section here to be a bit cooler so that any water that accidentally evaporated will fall back down and you'll collect only ethanol in the flask. Final one is chromatography. Chromatography is used to separate colored substances. We usually use it for mixtures of dyes. You have a beaker with a little bit of solvent in it, then your chromatography paper. You'll have drawn a baseline in pencil and spotted your mixture right here on the baseline. And then as the solvent moves up to nearly the top of the paper, any mixtures, any colors in the substance will separate based on how soluble they are. The most soluble one will go to the top because it moves with the water, and the least soluble one will be at the bottom. Now, chromatography often comes up in a little bit more detail. So up here, last section, we're going to talk about how to interpret a chromatogram. Here's what your chromatogram will look like. It has the baseline at the bottom and the solvent front at the top. And the calculation you can do is called an RF value, or retention factor, for any given substance. So if they ask you for this, you need to get your ruler out and do some measuring. They've asked us for substance B, so I'd measure the distance from the baseline up to substance B, and I got 20 millimeters. And then the same thing for the solvent. I got 32 millimeters. RF is really just a fraction. It wants to know what fraction of the paper, or what percentage of the paper did the substance move compared to the liquid. So ours is 20 out of 32, which is 0.63. You should write it as a decimal. Really, this means it moved 63% of the way up the paper. Question 2, which substances are found in the mixture? This one is just about finding the spots that match the spots in your mixture. Be careful in your wording. To get the mark here, you really need to use the word distance or height to show that you know what it means to match. So here's mixture X. 2 spots have moved up the paper, and they happen to each line up perfectly with one of our knowns. The top one lines up with known A, the bottom one lines up with known C, so there's your answer. You might notice there's a third spot here on the baseline that didn't move at all. That simply means it's not soluble in the solvent, so it stays attached to the paper. Next question, where should the solvent level be at the start of this experiment? You might think it would start right at the baseline with the spots, but that would actually be a huge disaster because all your spots would dissolve down into the liquid and nothing would move up the paper at all. We don't want that. You need to have the liquid somewhere around here, below the baseline, so that the spots will stay on their start and move up as the liquid moves up the page. Last question, what should be used to draw the baseline? Should always be pencil. You don't want to use pen. It needs to be something insoluble, because otherwise, as your liquid moves, your baseline would move, and you would be left with nothing to tell you where everything started from. All right, so that is a quick summary of solutions and separation, and you should now be ready for your multiple choice quiz.